right? Okay, sorry about that. So again, let me continue. So then this is GZ is this is equal to this summation, these two summations, and you combine this together, gives us 3 times minus 4 to the power of n minus 4 times 5 to the power of n, right? So that means the term here, yeah, the nth term is of course 3 times minus 4 of n, yeah, minus 4 times 5 power of n. All right, good. Any question? No? If not, let's have another example. This time it is slightly more complicated question. So suppose you are, let me shift this part a little bit there, and maybe add more space. Yes. Now, so the question is, you're given this GZ is 10Z plus 3 over 1 minus 2Z times 1 plus 4Z. Now, how do we solve this? We solve this, the idea is to use partial fraction. So essentially, want to write this in the form of A over 1 minus 2Z plus B over 1 plus 4Z. All right. Now, so the part we need to do is we need to find A and B here. So how do we do that? First, note that we could write the right-hand side here. Yeah, the right-hand side here is equal to 1 plus 4Z times A plus B, 1 minus 2Z times B over 1 minus 2Z times 1 plus 4Z. So therefore, by equating both sides, yeah, because the denominator is not 0, so this one is not 0. We assume that they're not 0. Yeah. So we could have that, we have that nz plus 3 is equal to 1 plus 4z times A plus 1 minus 2z times B. Yeah. Now, so remember what our aim is to somehow get this slightly simpler, closer form, right? Now then here, the right-hand side is actually A plus B plus 4ZA minus 2ZB, yeah, or A plus B plus you take out the Z, yeah, so that means you have 4A minus 2B Z. So that means this part equates to 3 and this part equates to 10. So that means we have that A plus B is 3 and also for A minus 2B is 10. Now, of course, this is equivalent to, this gives us, of course, this is 2A plus 2B is 6, yeah, together with this for A minus 2B is 10. So you sum them together, you get that 6A is 16, yeah. So A is 16 over 6, or if you divide it by 2, you get 8 over 3, yeah. Now you substitute these two to this equation, so you get A plus B is 3, so therefore B is 3 minus a, which is 3 minus 8 over 3, which gives us, of course, this easily solves into 16 over 3. Yeah. So as a result, yeah, as a result, yeah, I think the question is up to here, right? The partial fraction. But now the next part. This is not part of the question, but you might want to rewrite this. So therefore, GZ becomes, what do we have? We had earlier 10 plus 10z plus 3 over 1 minus 1 plus 4z times 1 minus 2z is equal to, what is the A? The A is yeah, the A is, of course, so 8 per 3 times 1 over 1, what was it, 1 minus 2z, yeah, like this, plus, what is B? B is 16 per 3 times 1 over 1 plus 4z, yeah, yeah, so let me put here. Now, of course, this could solve into the more explicit long generating function. This is equal to this is 2, right? So the ratio is 2. So this is 2 to the power of n z to the power of n, and this one is, the ratio is -4. So this is actually sum from n to z, from 0 to infinity, -4 for n z to the power of n. Yeah. So this gives us actually an is 1 over 3 times 2 to the power of n plus 6 over 33 times -4 to the power of n. Yeah, this could be simplified further, in fact, right? So that's how we solve that, right? Now, what about the next question? So we want to find, now this time we want to find the explicit form of the recurrence relation. So let's do it here. So let me use a different color for the pen now. Let's use blue this time. So given, so the question is, you're given an is for an minus 1 plus 3 to the power of n minus 1, where a0 is 1 and n is greater than 1. So find the explicit form, right? That's the question. So the first step is, of course, to change the recurrence relation into power series representation, right? So what is the power series representation? Where the power series representation is, should look like this, right? Sum of n from 0 to infinity, yeah, an z to the power of n, right? This is our basic form. Now we know that a0 is 1. All right. So also this relation holds. So if we write it down, so an for an minus 1 plus 3 to the power of n minus 1 becomes what? Well, becomes, you make this into sum. So sum and from 0 to infinity, yeah. Well, not 0 to infinity. Remember, this holds only when n is greater than 1. So therefore, instead of starting from 0, we should start from 1. So let me redo that. So actually, the correct answer is, I use the more thicker pen. So this some n from something. So a n z to the power of n. Now the right hand side holds only, this holds when n is greater than 1. So we need to use that as a limit. So that means this is sum of n from 1 to infinity, not from 0 here, right? Because of this. Yeah. So for an minus 1 plus 3 to the power of n minus 1 z to the power of n. So therefore, this is here. What about this? The when n is equal to 0, we already have that a0 is 1. We already have this. Right? Now the next step is to simplify that. The right hand side is equal to sum of n from 1 to infinity 4 times an minus 1 z to the power of n plus, of course, sum of n from 1 to infinity 3 to the power of n minus 1 z to the power. Yeah. Now, what is this? Well, let's change the left hand side first. So the left hand side is actually the same as this, from 0 to infinity an z to the power of n, and then minus a0. All right. So yeah, the whole thing here is the same as this, and you take out the a0, right? What about the right hand side? The right hand side, let's look at this part. This part, the index starts from n equals to 1, right? N is equal to 1 here, but a is actually starting from 0, right? Because if n is 1, then an minus 1 is a0, correct? So therefore, we could simply shift the index. So 4 times sum of n from 0 to infinity. Now we shift the index down. So that means if we subtract the index, the starting index by 1, then we add the subscript and the power here by 1. So if we subtract this by 1, then we add this by 1. Yeah, subtract this part, the index by 1. Then therefore the occurrence of n inside the summation, you add it by 1. So therefore this becomes an instead of an minus 1. Yeah. And the z to the power of n plus 1. Any question at this point? Is it clear at this point? If not, just let me clarify this. Remember, sum of n from 1 to infinity an minus 1 z to the power of n is actually a0 z to the power of 1 plus a2 z, sorry, a1 z to the square plus a2 z cube, and so on, right? So therefore, it's the same as starting from 0, but the power of z starts from 1, right? So n plus 1 here. Yeah. Now, what about the next step? The next part, the next term is this one. Yeah. Again, we subtract the index into by 1, so that you start from 0. So here, like this, from 0 to infinity. Now then you add this and this by 1, so you have 3 to the power of n z to the power of n plus 1. All right. Yeah. So that means, yeah, what is this? The left hand side here, let's call it the generating function, the power series is gz. Then here is gz minus a0, and this is what? 4z times the summation n z to the power of n plus, well, what about this one? Yeah, let's create this. This is what? This is z times sum of n from 0 to infinity, 3 to the power of n z to the power of n, right? And this is actually dz, right? So for z dz, and what about this one? This one is actually 1 over 1 minus 3z, right? So therefore plus z over 1 minus 3z. Good. Now what is so we put it down here, gz. What is a0? A0 is 1. So therefore you have, yeah. So therefore we move them together, we collect gz together. So therefore you have gz minus 4z gz is 1 plus z over 1 minus 3z. Yeah. Now, so what is gz then? This is gz times 1 for 1 minus 4z, 1 plus z over 1 minus 3z. Yeah. Which could be combined together. The right hand side is of course 1 minus 3z plus z, yeah, over 1 minus 3z. Now the right hand side here is actually 1 plus z is so 1 minus 2z over 1 minus 3z. Now therefore we obtain that gz is actually 1 minus 2z over 1 minus 4z times 1 minus 3z. All right. Now, what is our next step? Well, our next step is, yeah, solve this, yeah, into explicit form, right? So how do we solve this? Well, we use partial fraction. Yeah. So we want to write my gz. Yeah, we want to write it into a over 1 minus 4z plus b over 1 minus 3z. Yeah. Now remember, this part is equal to 1 minus 3z times a plus 1 minus 4z times b over 1 minus 4z times 1 minus 3z. Yeah. Now this means that 1 minus 2z is equal to 1 minus 3z times a plus 1 minus 4z times b, which is of course we simply multiply them together and you collect the similar terms together, so you get a plus b, yeah, plus minus 3za, yeah, plus minus 4zb. Now from here, this is equal to a plus b, yeah, plus z times minus 3a minus 4b. Yeah. So therefore, a plus b is 1. Yeah. And also minus 3a minus 4b is, what is it? Minus 2. Yeah. So here you get let me multiply this by 3. So you have that 3a plus 3b is 1, is 3, sorry. And then minus 3a minus 4b is minus 2. So, and then you sum them, you get that minus b is 1. So b is minus 1. So therefore a is 1 minus b, which is 2. Yeah, let's check, right? So a plus b is 1 clearly, and then minus 3a is minus 6, minus 4 is minus 3. Yeah, so you have it, right? So therefore we could write gz is actually what is a? A is 2 over 1 minus 4z plus what is b? Minus 1 over minus 3z. Now this could be solved easily by looking at the usual geometric series. Yeah, this allows us so 2 times sum of n from 0 to infinity. What is it? 4 to the power of n z to the power of n plus minus 1 times sum of n to infinity, 0 to infinity, 3 to the power of n z to the power of n. Yeah, remember this part, right? So if we combine them together, this is actually the summation. So 2 times 4 to the power of n. Yeah. And of course, minus 3 to the power of n. Yeah. Z to the power of n. Yeah. Okay. So this, that means we obtain the final solution. An is actually 2 times 4 to the power of n minus 3 to the power of n. If we check, remember a0 is 1. Should have been a1 is what? Sorry, for an minus 1 plus 3. So an is for an minus 1 plus 3 for minus 1. So this is, that means a1 is 4 times 1 plus 1. So that is 5. So if we check, can we check, is it correct? A0 is 1. Yes, correct. Yeah, 2 times 1 minus 1. And a1 is 2 times 4 minus 3, which is 5. Now, what about a2 here? A2 here is 4 times 5 plus 3 to the power of 1, which gives us 23. Now, what about this one? A2 is 2 times 16 minus 3 square. So 32 minus 9 is 23. So that is correct. Yeah, so it seems this is correct. So that's the solution. Yeah, for a complete solution. So you start from the steps. Just let me remind you. From this form, you write it into this form. Yeah. Remember, the lower bound is 1. So you start from 1 here. Yeah. And then in subsequent steps, what you do is you separate the summation into different parts, into separate parts. So for example, this is one, and this is another one. Remember, the index still starts from 1. Yeah. And then, yeah, the left-hand side here, try to write it down as GZ, where GZ is the general form. Now, because we start from 1, so therefore this is GZ minus A0. And then you could plug in A0. Similarly, on the left, you do a manipulation on the indices. So for example, this starts from 1. We change it into starting from 0 here, but an minus 1 is changed into an here. And z to the power of n will changes into z to the power of n plus 1. And so on. So you get the final form. So you get this form. Essentially, you get this as a closed form, and then from the closed form you do a partial fraction decomposition to get this. Yeah. Any question? No? If not, then let's have another example. This time the question is, let's insert space here. Yeah. For example, the question is here is, let me use the red pen. Question is, how many ways are there to put 18 indistinguishable balls into 3 distinguishable balls? That means we have 3 boxes, A, B, and C, for example, and you want to put this 18 into these 3 boxes, but the balls are the same, right? Yeah, the balls are the same, right? So you cannot distinguish the balls here. Now the condition is, if each box should contain at least 2 balls. Yeah, should contain at least 2 balls. Yeah. So here, the steps here is that, so we could represent, so how do we answer this? So represent box 1, count in box 1 as K1, count in box 2 as K2, and count in box 3 hold on a second. Yeah, count in box 3, correct. Yeah, count is box 3 as K3. So the problem is, yeah, problem can be formulated into, or as, find so into like this. So K1 plus K2 plus K3 must be 18, and also also that K1 is greater than or equal to 2, K2 is greater than or equal to 2, K3 is greater than or equal to 2, because each box should contain at least 2 balls. Now, what is our next step? So how many, because of this, right? So each box should have a maximum of how many balls? How many balls?
3.
Why is it 3?
Balls.
At most. A maximum of how many balls?
16.
Why 16?
Because we need 2 balls on the other boxes.
Yeah, we need 2 balls in the other 2 boxes, right? Not just 1 box, if I remember. So a maximum of 14, not 16. Yeah. You see that? Yeah, because if a box has more than 14 balls, then we are only left with uh, with with less than 4 balls, which means one box has less than 2 balls, yeah, which violates the requirement, right? The condition. So that means each box should have a maximum of 14. Yeah. Now, so what is next? Each box should have a maximum of 14. So the next step is to 1 second. Something is weird with my um so we know that that each case should have a maximum. So each case should be at most 14. So therefore we could write each box, yeah, each box can be represented by the following series, right? By z square, meaning that this is the series, yeah, represented by this up to z to the power of 14, yeah. And so to put 18 balls, yeah, into 3 boxes, here we need to find the coefficient of z to the power of 18 from this expression. So z z square plus z cube plus z 15, yeah, yeah, and times z square. This is for the second box. And this is for the third box. Now 14. Now, of course, to solve this, we need to somehow multiply them together. So this is the difficult part. Yeah. For example, if you take 2 here, then it could only be paired with 14 here. Yeah. Yeah. And also, for example, to get 18, right? So 2 here, 3 here, and then 13 here. Yeah. And so on. Yeah. So you multiply them together and find the coefficient of z to the power of 18. Right. Any question? No? Okay. If not, then let's try the final problem in this squeeze. What's this? Let's do this. Let's use the black marker again this time. Here, yeah, how many ways are there to choose 6 letters from the string Garbarata? Remember, there are 1, 2, 3, 4 A's there. Yeah. So how do we solve this? So use generating function to represent each letter. Represent ways to choose each letter. So for G, yeah, what about G? So how do we solve this? So the idea here is, let's say, suppose X1 represent ways to choose XG, yeah, to choose G, then XA ways to choose A, and then XR is ways to choose, number of ways to choose R, and then we have what would be the other letter? G, A, R, B, and T, right? G, A, R. So we have XB, two ways to choose B, and finally XT is the kind of ways to choose T, right? So now the constraint is, of course, that XG plus XR. So we need to do a combination from the 3, right? So from the 5 variables here. So XR plus XA plus XB plus XT must be 6. Yeah. And you know that, well, XG can only be at most 1. So 0, XG, 1. Also XR is also, there is only 1, 2, right? So it could be, so XR could be 2, and then XA could be 1, 2, 3, 4. So XA, and then XB. What about XB? XB, there's only 1. So, and then T, there is also 1, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. So, and we have XT is only 1, right? So now, yeah, now this becomes the generating function could be defined in a way that is that corresponds to the count, right? So essentially, the choices for XG, so that means you have xg, yeah, could be represented by the generating function sum of n n from 0 to 0 to infinity, not to infinity, sorry, from 0 to 1, and this time is z to the power of I to the power of n over n factorial. Yeah. What about xr is similarly up to 2 z to the power of n factorial. What about xa is sum of n from 0 to 4 z to the power of n 4 factorial. Xb is sum n to from 0 to 1 z to the power of n factorial, and finally xt sum from n from 0 to 1 z to the power of n over n factorial. Yeah. So now, and of course, the result is, yeah, the count, the torcon here is xg times xr times xa times xb times xt, yeah. So that is that sum, and then find coefficient of z to the power of 6, because you want to find 6 letters. Yeah. Okay. So any question so far? There are a few parts of the question that are not discussed here. I suggest you to also discuss the solution to with the assistants outside class, so they will be helpful, right? Yeah. With that, any question for today's session?
No, sir.
No. Okay. So for recurrency relation, the main thing is do a lot of exercises. Yeah. Try to do a lot of exercises, and you'll get by more having more examples, you get the hang of it. All right. So with that, let me finish the session today. I'll see you guys on Monday. All right. Thank you, and bye-bye.